In the last couple of videos, I introduced you to the idea of freefall motion. Freefall motion is motion in which the only force acting on the object is the gravitational force. And we've also learned that an object which is free falling near the Earth's surface is accelerating downward at 9.8 meters per second per second. In this video, we're going to do our first example problem involving free falling motion. And we're going to be using the same kinematics handout that we used in some of the earlier videos, namely this one right here. So let's look at the problem, and then we will dive into using the handout to guide us through the solution. So we have a building here, and there is a window 40 meters above ground level. A rock is going to be launched from the ground. So here's a rock being launched upward. And we are told that the rock passes this window at a speed of 30 meters per second. There are three parts to the problem. Part A asks for the rock's launch speed. Part B asks what is the greatest height attained by the rock. So what's the maximum height before it turns around and comes back down? And part C, what is the total time that the rock spends in motion from the launch, going up to the top, and then coming back down and hitting the ground? Okay, so step one is to draw a clear sketch illustrating the problem. So we have the beginnings of a sketch right there. Step two, draw a coordinate system. The coordinate system should have a clearly marked origin. Now, I have already drawn in the y-axis here. My preference for this kind of problem is to have the y-axis pointing up. I also like to put the origin of the y-axis at the lowest point in the problem. That way, the y-coordinate is always either positive or zero, and we don't have to worry about negative y-coordinates introducing minus signs into our problem that can unnecessarily trip us up. That's step two. Step three, identify and number the moments of interest. At this point in the problem, I'd invite you to pause the video and see if you can identify and number the moments of interest correctly on your own. In order to do that correctly, you'll need to consider all three parts of the problem that we're solving for, and then you can go into the figure, draw in the moments of interest, and then number them as well. Okay, in this problem, we actually have 4 moments of interest. Now, the first moment of interest would be the launch. We'll call that moment 0. Now, strictly speaking, that first moment of 0 is not actually the launch. We are not thinking about that situation where that person standing near the ground is actually starting to throw the rock upward. As that person is launching the rock to get it to start moving upward, that person is exerting a force on the rock. And if you have some outside force acting on the rock, then you are not in a free fall process. So this moment right here, moment of interest 0, that would be immediately after the release of the rock by whoever's launching it, so that we have already entered the free fall part of the motion. Okay, so that's moment 0. The next moment is going to be as the rock passes the window. At that point, I presume moving slower, so I draw this arrow a little smaller. Let's call that moment 1. Then the rock is going to reach the highest point somewhere here. Let's call that moment 2. That's the highest point. And then the rock is going to turn around and head back towards the ground. And since we are looking for the total time in motion, our last moment of interest is going to be right here, right before the rock hits the ground. Okay. Similar to what I told you about the launch, moment of interest 4 does not coincide to the moment the rock actually hits the ground, because once the rock hits the ground exerts a force on the rock, and we are no longer dealing with free fall motion. So this would be the moment immediately before the rock hits the ground. Let's go to moment 4. So we have option A, constant velocity problem. This is not a constant velocity problem. This is a constant acceleration problem because a free-falling object near the Earth's surface accelerates down at 9.8 meters per second per second. So as we practiced in some of the earlier problems, we're going to go to each of those moments of interest and put in symbols for time, position, and velocity. At this point, the figure is already a little bit crowded, so we're going to have to be a little bit clever about how we squeeze all of those kinematic variables into the figure. So let's just start with moment 2. So moment 2, we're going to have time 2, y coordinate 2, velocity 2, moment 1, we're going to have time 1, y coordinate 1, velocity 1, and then down here at the bottom, there's 2 moments of interest we have to squeeze in. So let's try and be clever about that. So for moment 0, we have time 0, y coordinate 0, and velocity 0. And I'll put the kinematic variables for moment 4 over here. So we would have, oops, I noticed that I called that 4. I should have called it 3. So I'll put the kinematic variables for moment 3 over here. We have time 3, y coordinate 3, velocity 3. It also says write the acceleration off to the side. Now, this is starting to be a full picture with all these kinematic variables and so forth. I'm going to go put the acceleration here. I'm going to put a y subscript there just out of habit for reasons that will become clear later on. So I'm going to call this a sub y. Now, the y-axis is pointing up, but the acceleration is towards the downward. So this is a negative acceleration, ay equals minus 9.8 meters per second squared. Okay, so now we have done step 4. So now why don't you pause the video again and give step 5 a try on your own. Go through and put in any of those variables whose values we can figure out without actually doing any calculation. Okay, so the rock is launched, and we might as well say the rock is launched at time 0. The rock is launched from ground level. That's where we put the origin. And we don't know the launch speed. That's part of what we're trying to figure out here in part A. Now, when the rock passes the window, we know the window is 40 meters above ground level. The speed of the rock as it passes the window is 30 meters per second. We do not know the time. We'll leave that blank. Now, up here at the top, the only thing we know is the velocity. If you toss an object straight up into the air, then on the way up, the object has an upward velocity, which would be positive for this coordinate axis. On the way down, the object has a downward velocity, which would be negative for this coordinate axis. So the only moment when the object has a velocity of 0 is when it is at the highest point. So I put in 0 here. And we come to this moment where the rock arrives at the ground. And the only thing we can fill in right now would be the coordinate 0. So that's our setup. Now we're going to solve the problem by applying these equations here, which are familiar from our previous example problems with objects moving at constant acceleration. I've written out these equations in the same form we had them before, where we are using the x-coordinate as our position axis. Here, we're using a y-axis, but no problem. If we apply these equations to this problem, we'll just turn the x's into y's. Let's go to part A. It asks, what was the rock's launch speed? If we go to the figure, what we are being asked for here is V0. In a problem involving an object using constant acceleration, we can use these formulas here to connect one moment to any other moment, as long as we have constant acceleration all the way between those two moments. Now, in this problem, we have constant acceleration throughout. So we have a constant downward acceleration of 9.8 meters per second, all the way from the moment of launch to the moment the rocket gets back to the ground. So we can use these constant acceleration equations to connect any moment to any other moment. We know for part A that we want to use moment 0 because we're looking for velocity 0. So you can ask yourselves, which other moment should we connect to moment 0 in order to get this launch velocity? Now here you can pause the video and maybe even try and solve part A on your own before rejoining the video. Here's how I think of this. If I look at the other moments here, moments 1, 2, and 3, the moment that we have the most other information about is moment 1, right? In moment 1, we know 2 of those 3 kinematic variables. In moments 2 and 3, we only have 1 each. So we are probably going to be able to solve for V0 the easiest by connecting moment 0 to moment 1. So we go through the list here and see if we can find an equation connecting moment 0 to moment 1 where the only unknown is V0. See if you can do that. Okay, so perhaps you noticed that if you look at equation 4, we can just take it as written, except changing x's into y's, connect moment 0 to moment 1, and then from that we can solve for V0. Okay, so I'll just copy equation 4 over. We have V1 squared equals V0 squared plus 2a, I'll call it ay, and then instead of x1 minus x0, y1 minus y0. We are trying to solve here for V0. So let's see here. Y0 is 0. I guess there's no other zeros. So we just have to push stuff around and isolate the V0. So not actually that bad. We're going to take that 2ay, y1, move it to the left, where it picks up a minus sign. Okay, now I'm going to flip the sides and take the square root of both sides. That gives me V0 equals V1 squared minus 2ay, y1 square root. As always, we're going to make our substitutions as numerical values along with units. So let me put in the V1. That is 30 meters per second squared minus 2ay minus 9.8 meters per second squared. And then y1 was 40 meters. Punching this into my calculator, I get 41.0. Now, as far as the unit, notice that both terms inside the square root have units of meters squared over second squared. So meters squared over second squared here, meters squared over second squared here, square root that, you get meters per second as we would expect for a velocity. So that's part A. And now that we got that, let's go ahead and put that into the sheet so we can use it later. Part B, what is the greatest height attained by the rock? So let me bring this sheet back again. Here we are looking for y2. Here we are looking for y2. So as usual, you're going to think about taking one of these equations so that it connects some other moment to y2. The question then is just which moment. So you can try this on your own. Find an equation that connects moment 2 to some other moment where when you write that equation properly, y2 is the only unknown appearing. So try that on your own and then rejoin the video. You can do this two ways. You could connect moment 2 to moment 1. Or you could connect moment 2 to moment 0. My preference would be to connect moment 2 to moment 0, because if you look at moment 0 here, there are more things that are already 0, so that might simplify the calculation. Okay, so I'm going to take moment 4 and write it so that it connects moment 0 and moment 2. Okay, that gives us v2 squared equals v0 squared plus 2 a y2 minus y0. v2 is 0. Then we're going to take v0 squared, move it to the left where it picks up a minus sign. Then take that 2ay and divide it into the denominator over here. We now have minus v0 squared over 2ay equals y2 minus y0. Oh, y0 was also 0. Okay, so we have y2 equals minus v0 squared over 2ay. Let's make our substitutions. Minus, and then v0 was 41.0 meters per second squared. Divide by 2, ay minus 9.8 meters per second squared. I'm going to punch this into my calculator because I have a different calculation in my notes. Okay, when I did it this way, it actually came out a little different. I got 85.8 as the numerical value. Now, as far as the unit, we should always calculate our unit. So look at the numerator there. The numerator is meters squared over seconds squared. The denominator is meters over seconds squared. Second squared cancels second squared. Meters squared over meters gives meters. So we have y2 equals 85.8 meters, meters being the correct unit for a y-coordinate. Let's go to the figure and put that in. Last part of the problem, how much time does the rock spend in motion? Well, if the rock is free falling, then it is going to come back down to the ground at the exact same speed that it was launched, which means that if the velocity of the rock right after the launch was 41 meters per second, then when it gets back down to the ground, the velocity will be minus 41 meters per second. In other words, same speed, opposite direction. With that, see if you can find an equation which connects moment 0 to moment 3, where the only unknown is time 3. So pause the video, give that a shot on your own, and then rejoin the video. So perhaps you noticed that if you take equation 2 and write equation 2 so that you connect moment 0 to moment 3, then the only unknown will be time 3. Okay, so I'm going to use equation 2, but I'm connecting moment 0 to moment 3, so I have v3 equals v0 plus ay. Delta t, if you're going from moment 0 to moment 3, would be t3 minus t0. t0 is 0, and we are solving for t3. So just take that v0, move it to the left where it picks up a minus sign, then divide by ay. All of that equals t3. So now flipping the sides and then substituting, we have v3 minus 41 meters per second minus v0, 41 meters per second, all over ay minus 9.8 meters per second squared. And I'll let you do the calculation of the unit on your own this time. I got 8.4 seconds. So now we have done our first example problem involving free fall motion.